Hi everyone, my name is Wei Ting and I'm a PhD student in the School of Pharmacy at the University of Sydney. So today I'm going to share to all of you about my project, which is about the development of dry powder formulations of cannabidiol with enhanced solubility. So let's start with cannabis. So cannabis is a herbal medication that has been used for thousands of years. It contains more than 500 components, including terpenes, flavonoids, and cannabinoids. There are psychoactive cannabinoids such as delta-9 tetrahydrocannabinol, and also non-psychoactive cannabinoids, for example, cannabidiol or CBD. CBD is the second most prevalent neutral cannabinoid in cannabis. It has a lot of potential pharmacological actions, for example, being anti-inflammatory, antioxidant, and being immunomodulatory. It is most established as a treatment of seizures associated with Lennox-Gastaut and Dravet syndromes. For these indications, FDA approved Epidiolex, an oral CBD solution, in June 2018. This vehicle is sesame oil and dehydrated alcohol, and this brings us to the formulation challenges of CBD. So the first challenge is about the low aqueous solubility. CBD is a hydrophobic drug with reported solubility in water at about 0.1 microgram per ml. To improve the solubility, we choose to use micelles. So micelles have hydrophilic head and hydrophobic tails, which can entrap the drug into the core and keep it in solution. To form micelle, we need surfactants. And indeed, in our lungs, there are endogenous surfactants, which mainly consist of phospholipids. One of them is dipalmitoyl phosphatidylethylamine, or DPPC. It is also an active ingredient in treating respiratory distress syndrome in preterm infants, and also can act as an excipient to improve the dispersion of dry powder formulations. And other challenge is about the poor chemical stability of CBD in solution. So we know that CBD is very prone to degradation by light, temperature, and oxygen. And studies have shown that CBD has better stability in powder form than in solutions. But then why do we want to change the route of administration to pulmonary delivery? So from previous literature, we know that the oral bioavailability of CBD is as low as 6%, suggesting that this is an inefficient route of administration. And pulmonary delivery is actually a promising alternative, especially when the most common delivery methods of cannabis is actually by inhalation via smoking and vaporizing. However, these two methods require heat, which induces chemical changes, making that not ideal to deliver cannabis. But then nonetheless, they successfully increased the bioavailability to 31%, and this demonstrates that pulmonary delivery can efficiently deliver cannabis to the body. The aim of this study is to develop inhalable dry powder formulations of CBD with enhanced solubility. So we put CBD together with DPPC and also one of the hydrophilic blocking agents, mannitol or trehalose dihydrate, as our formulation. So DPPC is a surfactant and works as a solubility and dispersion enhancer in this formulation. For mannitol and trehalose dihydrates, they are both hydrophilic blocking agents to improve powder wettability. So to produce the powder, we use spray freeze drying. So we dissolve all the ingredients into a solution, and then we atomize the solution into droplets and let it fall into liquid nitrogen, which can snap freeze the droplets into solid particles. And then we put the particles into a freeze dryer and allow the solvent to sublime under vacuum. The resultant spray freeze dry powder will be porous, which benefits the dispersion. After we produce the powder, we determine the crystallinity, solubility, and also the aerodynamic particle size distribution for the powders. So in terms of the crystallinity test, we use the X-ray powder diffraction. So the X-ray penetrates the crystal and then diffract. The pattern mainly depends on the structure of the crystal lattice. Then the X-ray diffractometer records the scatter intensity from 5 to 50 degrees. For the solubility test, we put excess powders into 0.002% 280 in phosphate buffer saline, and we kept the solution stirring at 37 degrees Celsius for 2 hours. So the buffer solution and the temperature is to mimic human physiological conditions, and 280 is added for analytical purpose. For the aerodynamic particle size distribution, we used the next generation impactor. So we loaded approximately 5 mg of powder inside the capsule and then put it into the osmohaler and get the capsule pierced. Then the osmohaler with capsule connected to this side of the next generation impactor, while the other end of the NGI connected to a pump to generate the dispersion force. This right angle flow here is to mimic human throat for impaction. So we disperse the powder at 4 kPa drop and allowing 4 liters of air to pass through the inhalers. So after we disperse the powder, we chemically quantify the amount of drugs at different parts in the setup, and then we calculate the emitted fraction and the fine particle fraction. So the emitted fraction is the proportion of particles that exceeded the inhaler. The fine particle fraction is defined as the proportion of particles smaller than 5 micron in aerodynamic diameter. So the higher the fine particle fraction, the more small particles can reach the deep lung and therefore may potentially have a higher therapeutic effect. In this slide, it shows the results of the X-ray powder diffraction. So those with peaks are crystalline, while those without peaks are amorphous. So we can see that all raw materials and the mannitol formulation were crystalline, but then it's hard to determine the crystallinity of each component inside the mannitol formulation. So that's because the peak positions are different, suggesting that they have different crystallinity form. At the same time, they have low intensity is because of the low proportion inside the formulation. For the Charles formulation, it is amorphous, and generally speaking, amorphous formulation dissolve faster and higher than crystalline formulation, and this agrees with the results of our solubility test. So we can see that raw CBD has the lowest concentration among the three and was significantly lower than the two formulations. So although the mannitol formulation and the Charles formulation were not significantly different from one another, we can see that mannitol formulation actually has a lower concentration than the Charles formulation. So the differences in solubility can be explained by their crystallinity. So from the X-ray diffraction data, we know that raw CBD and the mannitol formulation are both crystalline, while the Charles formulation is amorphous. So the mannitol in the formulation actually formed an orderly packed structure on its own, leaving DPPC and CBD out of the matrix, and therefore it provided limited enhancement in the wetting and dissolution of CBD. This suggested that its solubility was increased mainly by DPPC. So in contrast, CBD and DPPC fitted well into the glassy matrix of the amorphous formulation of the Charles. So therefore, CBD in that powder was wetted better and dissolved easier, reaching a higher saturated concentration. In terms of the aerodynamic particle size distribution, there are less Charles formulation retained inside the capsule and also less deposit at stage 1. But there are more Charles formulation deposited from stage 2 onwards, suggesting that it may have a higher fine particle fraction than the mannitol formulation. So for the recovery, both of them are close to 100%. It means that all the drugs are accounted for in the experimental parts. For both formulations, around 90% of them exceeded the inhalers and they are not significantly different. But their fine particle fraction are significantly different. The Charles had a significantly higher fine particle fraction than the mannitol formulation. It means that potentially Charles formulation could achieve a stronger therapeutic effect than the mannitol formulation. In conclusion, we developed inhalable CBD powders with enhanced solubility. They have acceptable aerodynamic performance for pulmonary delivery and also significantly enhanced the aqueous solubility of CBD, which may lead to higher drug absorption from the lungs. The powder containing Charles performed better overall than that containing mannitol due to its higher solubility of CBD and also better aerosol performance. At the very end, I would like to thank my supervisors, Dr. Philip Kwok and Professor Kim Chen, for all their guidance and advice during this project. I would also like to thank Associate Professor Jonathan Arnold and his postdoc, Dr. Lindsay Anderson. They are from the Lambus Initiative. I really appreciate their help during this project. I would also like to thank everyone else in the Advanced Drug Delivery Group. And that's the end of my presentation. Thank you so much.